Hi guys, in this video I'll be talking about Darcy's law and how we can derive the dimensions for permeability, which is a derived unit or variable that comes from Darcy's law. So first of all, while I'm going to be drawing the experimental setup for Darcy's law over here, I want to talk a little bit about Darcy's law. So Darcy's law is a mathematical statement that describes the flow of a fluid through a porous medium, and this was based on Henry Darcy's experiments of the flow of water through beds of sand. So who was Henry Darcy? Well, Henry Darcy was a French engineer who was renowned for obviously for coming up with this law. And this law today forms the basis of hydrogeology, which is a branch of earth sciences and finds extensive use in the petroleum sciences and petroleum engineering. So, since this is talking about the flow of something through something else, as you might have guessed, it is actually analogous to some other types of units or types of laws, which are Fourier's law for um, heat conduction, Ohm's law for electrical networks, and Fick's law for diffusion. All right, great. Let's get into it for Darcy's law. So originally, this was derived experimentally by Henry Darcy, who, well, I won't be getting into the experiments for today, but let's go through the experimental setup that he used. So what did Henry Darcy do? So imagine that we had some kind of pathway which was filled with some kind of sand, or it could be any kind of sediments, but in the case of his experiments, it was sand. And it was packed in such a way that it was evenly distributed throughout the whole cylinder. So then, if we were to pass a fluid through it with a flow rate of Q, possessing a viscosity of mu through a length of L with a pressure at the inlet of P1 and a pressure at the outlet of P2, where P1 has to be larger than P2, and that has a constant cross-sectional area, Darcy found that the flow rate is proportional to the difference in pressures. So that would be, let me get the colors right, the difference in pressure over the length. So this is known as the pressure gradient. Okay, so this can also be rewritten as follows. Q is proportional to dou P over dou L. If I can get the colors right over here, dou P over dou L. Alright, so later this equation was generalized to be in this form, where Q is equal to some permeability K. So since permeability is the unit that we don't know, let's give it the dark blue. Q equals K. Let me check the thickness on that. Yeah, that's right. K over mu times the cross-sectional area to flow over the pressure times by the pressure gradient. So dou P over dou L. Alright, so that's a lot of colors over here. So to get a better grasp on what all of these things mean, and to derive the units, the dimensions for permeability, which is this innocent looking K over here, let's actually rearrange this equation to get K on one side. So K is going to be equal to Q mu, if I can get the colors right, Q mu divided by dou P over dou L, which I'm just going to quickly draw over here. It's an orange. And divided by A as well. Alright, so at this point, for us to be able to perform dimensional analysis to get the dimensions of K, let's actually take out what the dimensions of all of these individual variables are. So Q, which is the volumetric flow rate, well, volumetric flow rate is just some volume over time, which can be written as L3 over T, L to the power 3 over T. And by the way, for this analysis, we'll be using the MLT system. I'm just gonna write that down, note that down real quick. We'll be using the MLT system, mass, length, time, yeah, not FLT, which is force, length, and time. All right, so mu. Mu is typically measured in centipoise in the field, which is just millipascal seconds, which is this milli stands for 1 times 10 to the power of minus 3. And pascals are a unit of pressure, whereas seconds are a unit of time. So our goal now is to find out what the units of our intermediate variables are. So pressure, well, let's recall the formula for pressure. That would be force over area. And force is some mass times some acceleration. So we can write it in this form. Dimensionally speaking, mass is capital M. Acceleration is given by length divided by time squared, which is LT minus 2. And A is area, which is given by L to the power of 2. All told, this can be rewritten as ml minus 1 to the t times t to the minus 2. So time is just, well, time is simple, that's just t. So putting all of this together, we get units of mu of ml minus 1 t minus 2 multiplied by t, which gives us ml minus 1 t minus 1. Alright, moving on. Let's look at the area. So area is simple. It just has dimensions of length squared and dou p over dou L. Well, dou p is just pressure, which we already have investigated just now and found it to be ml minus 1 t minus 2, whereas dou L is just a difference in length, so that just has units of L. So now let's put everything together. Hopefully we'll be able to see everything over here. Put this in this nice little corner over here. So K is dimensionally equivalent to the volumetric flow rate multiplied by, so what was the units of viscosity again? ml minus 1, t minus 1. Let's write that over here, ml minus 1, t minus 1. Put the multiplication symbol over here. Put that over here and put this line in preparation for dou p over dou L. So A is L squared. We have here the units of pressure, ml minus 1, t minus 2. It's a minus 1 by the way. And dou p over dou L is just L. So if I recall correctly, that was an orange. Right. Okay, so now putting everything together, let's actually scoosh down a little bit so we have a little bit more space. Hopefully the scrolling hasn't annoyed you by this point. So we can write that K is, okay, let's perform some simplifications over here while we can. Let's use lime for that. So let's have a look. These m's cancel out. These t minus 1s combine to make t minus 2. This L minus 1 over here gets cancelled by this L over here. So we can cancel those out. This L minus 1 will multiply with this L power 2 to just give L. And these, so let's write what all of that down is using just this dark blue. So this will give us L3 t minus 2 at the top before simplifications. And at the bottom, we will have L squared. So remember that we L squared. So these L minus 1s have already been cancelled. Okay, have an L minus 1 here. And we have a t minus 2 here. Alright, so what does all this simplify to? All this simplifies neatly, so these t minus 2's cancel. This L minus 1 will just give us L3 divided by L, which finally is equivalent to L squared. So there we have it. Performing dimensional analysis, we managed to show that the units, the dimensions of permeability are length squared. So that's the end of this video. And as a little tidbit to the end, this is a very important equation in petroleum engineering, Darcy's law, especially after Muscat and Maris have generalized it for multi-phase flow and That has now formed an analytical foundation for reservoir engineering. So that's the end of this video. I hope you like, comment, and subscribe, and click the bell icon to activate notifications. Thank you.